Okay, continuing our lesson on carbohydrates. This is where we left off. Okay, we said that earlier that epimers were diastereomers that differ only in the configuration of one chiral center. In the presence of base, glucose and other monosaccharides can undergo epimerization. Okay, and here's how that works. Okay, so OH removes the hydrogen from carbon number 2. In the previous chapter, we talked about alpha hydrogens and their acidity. Okay, when we remove this, we now have an enolate. And the oxygen then pushes back, and the alkene removes a proton from water. We get the OH back. Okay, this is a reaction that we saw in the previous chapter. So stereochemistry is lost when we, at least at that chiral center, when we form this enolate. So glucose is in equilibrium with mannose under basic conditions. Okay, another type of rearrangement is what's called the enediol rearrangement, and this can also take place in basic solution. So we start off as before. OH removes this hydrogen. We get the enol, or enolate, I should say, and then the enolate can rearrange to this enediol. Okay, it's an ene, and then both of the alkene carbons have an OH. Okay, this undergoes deprotonation and deprotonation of water, and then we end up with fructose. So glucose can also be converted to fructose in basic solution. Okay, in this case, the carbonyl position shifts. Okay, so if you're doing carbohydrate chemistry, usually you want to use acidic or neutral solutions of sugar to prevent this rearrangement. Okay, there are some situations, such as the Tollens and the Benedict's test, where you actually do carry this out in basic solution, but that's a simple chemical test. Okay, so reduction of simple sugars. Okay, since aldose and ketoses are, after all, aldehydes and ketones, the carbonyl group can be reduced by sodium borohydride or catalytic hydrogenation. And for the resulting product, we name the sugar alcohol by adding etol to the root name for the sugar. Reduction of D-glucose produces D-glucitol, which is more commonly known as D-sorbitol. Reduction of D-fructose produces a mixture of D-glucitol and D-mannitol. Okay, because there was not a chiral center on carbon number 2 originally, where the ketone was, and this reduction is non-stereospecific, so we'll get both configurations at carbon number 2 when we form the alcohol. Okay, and that's what this slide is showing. So here is the open chain ketone. We reduce the ketone functional group, and then we get a mixture of alditols. D-glucitol and D-mannitol are used as artificial sweeteners in where you most frequently find them is for example, in gum. They are more difficult to digest than mannose or glucose, and so they are considered lower calorie. Okay, aldoses can be oxidized to carboxylic acids using bromine and water. Okay, all of the alcohols are unaffected, only the aldehyde is oxidized. And this gives what's called an aldonic acid. Okay, if we have a ketose, the monosaccharide is not oxidized by bromine water. Okay, nitric acid oxidizes not only aldehydes, but also primary alcohol groups, terminal CH2OH groups. Okay, so here's an example. Glucose, for glucose, the aldehyde is oxidized and the primary alcohol is also oxidized. If we had a ketose, okay, this if this, for example, were a ketone, this is a primary alcohol, this is a primary alcohol. Okay, the ketone would stay the ketone, but then the primary alcohol would get oxidized to a carboxylic acid, and so would the primary alcohol on the last carbon. Okay, oxidation by the Tollens reagent. Okay, this is a reaction that we commonly do in lab. Here we use the diamine silver complex. Okay, so we start out by dissolving silver nitrate in water, and when we make the solution basic, the silver precipitates as silver oxide, Ag2O. But then when you add ammonia, the ammonia forms a soluble complex with the silver, even in basic solution. And this is what's called the Tollens reagent. The Tollens reagent will oxidize aldehydes to carboxylates. Okay, it's ammonium carboxylates rather than carboxylic acids, because this is carried out in strongly basic solution. Okay, so silver plus 1 gets reduced to silver 0, and so a silver mirror forms on the test tube or flask. Okay, and this is a simple chemical test for what are called reducing sugars. It's a qualitative test for the identification of aldehydes. Okay, it turns out that fructose, okay, which is a ketose, actually undergoes the enediol rearrangement. Okay, since this is in basic solution, it will undergo the enediol rearrangement to glucose, which will then react with the Tollens reagent. Okay, non-reducing sugars will have an acetal at the anomeric carbon. Okay, if you have a hemiacetal, glucose exists mostly as the hemiacetal in solution, and it's continuously opening and closing. But once it does open, then the aldehyde will react. There's another test for reducing sugars. It's called the Benedict's test, and this uses a solution of copper 2, which has been complexed with citrate, basic solution, and that produces a reddish-brown precipitate of copper 1 oxide for a positive test. Okay, but if you have an acetal group, then acetals are more stable than hemiacetals, and this ring won't continuously open and close. And so this won't react with Tholins or Benedict's reagent. Glycosides are acetals, which are stable in base, so they won't react with the Tholins reagent. Disaccharides and polysaccharides are also acetals, and they are non-reducing sugars. Okay, so to form a glucoside, okay, if we start out with the for example, the alpha-D-glucopyranose. This could be either alpha or beta. Using methanol and an acid catalyst, we can produce the methyl ether at the anomeric carbon. And this is called an aglycone. So here is the alpha form, and this is the beta form. Okay, but once we form those, these don't readily interconvert in basic solution. Okay, in acidic solution with an excess of water, we can hydrolyze the ether group at the anomeric carbon. Okay, aglycone is the term used for the group that's bonded to the anomeric carbon. Okay, something other than OH. Okay, these are some other aglycones. Okay, so here we have ethyl alpha-D glucopyranoside. Okay, so we've replaced the hydrogen with an ethyl group. Nucleosides are actually aglycones. Okay, so this is ribose here, and this is the anomeric carbon, and the OH is replaced by this base cytosine, and this is now called cytidine, which is a nucleoside. Okay, this is here's another ether, which is an aglycone. This is salicin from willow bark, from which we get salicylic acid. Some aglycones are bonded through an oxygen atom. That's a true acetal. Others are bonded through other atoms, such as nitrogen. Okay, in order to form methyl ethers on all of the OHs, okay, typically what we'll do is we'll use an excess of iodomethane, and then we use silver oxide to precipitate the iodide, which is released, and that drives the reaction to completion. Okay, so we end up methylating all of the OHs. And these methylated sugars are stable in base. Okay, we can also esterify typically using acetic anhydride, using an excess of acetic anhydride, and then using pyridine as the base to neutralize the acetic acid byproduct. Okay, so we end up putting acetate ester on all of these OH groups. Okay, and these esters can be readily crystallized and purified. Okay, next we'll look at osazone formation. Historically, this has been used to identify mono and some disaccharides. Most osazones are easily crystallized and exhibit sharp melting points. Okay, that is in contrast to the original sugars, which typically soften and form a syrup over a large temperature range, and it's difficult to get melting point data for many mono and disaccharides. Okay, so these melting points provide valuable clues to the identification and comparison of sugars. Okay, so this uses 2 molecules of phenylhydrazine. And actually, to carry this out, you need 3 equivalents of phenylhydrazine because one is involved in an oxidation. Okay, so 2 molecules condense, and both C1 and C2 have been converted to phenylhydrazones. Okay, and we can do this with aldoses and ketoses. Okay, so one equivalent oxidizes this to an aldehyde and this one to a ketone. And this is a reaction we talked about at least we introduced in chapter 18. Okay, we split out water, we replace the CO double bond with a CN double bond. But with aldoses and ketoses, we form this phenylhydrazone on both carbons 1 and 2. Okay, these are yellow crystalline derivatives. And we can use these derivatives once they're crystallized and dried to identify the particular sugar. Okay, it turns out that glucose and fructose actually give the same phenylhydrazone. But you can identify the sugar based not only on the specific melting point, but also if these crystals are viewed under a microscope, the different phenylhydrazone derivatives or osazone derivatives have different crystal shapes. Okay, I'm going to just very briefly mention the rough degradation. I'm not going to say much about it, but we can remove carbons one at a time. Okay, this is and this is another one I'm just going to mention very briefly. Okay, so this should be a familiar reaction. KCN. Okay, we cyanide attacks the carbonyl. We form this cyanohydrin, and then when we reduce the cyanohydrin, okay, using a diluted catalyst, okay, that reduces the nitrile to an imine, okay, which is then hydrolyzed to a longer chain aldose. Okay, one disadvantage, of course, is that this reaction is not stereospecific, so we'll get both isomers at both configurations at carbon number 2. Okay, and then I'm not going to say too much about Fisher's proof, except that when he was looking at deglyceraldehyde, he happened to guess correctly that the OH was on the right side in the Fisher projection of deglyceraldehyde. Okay, at the time, he didn't really have a way of knowing that, but he just happened to guess correctly. Okay, and then this is mostly historical. I won't say too much about it. Hayworth determined the pyranose structure of glucose in 1926. Periodic cleavage of carbohydrates can sometimes be used for aid in identification. Okay, we talked about this earlier. If we have a diol, we can cleave the carbon bond between the two alcohols using periodic acid, HiO4. Okay, in the next lesson, we'll look at disaccharides.